So, good afternoon, students. This is Arvind, Assistant Professor, Department of Trustee, DBS, So, in the previous sessions, I discussed about EMF equation of the single phase transformer and some transformer ratios discussed, and I discussed it, and some user problems also we discussed it. And now in this class, I'm going to discuss the phasor diagrams of the single phase transformer. So, that too, for when the transformer is a no-load condition and when the transformer is a on-load condition. For both the cases, we have to explain the phasor diagrams of a single phase transformer. Okay. Firstly, I am going to take the phasor diagrams of a transformer. Firstly, the introduction of this phasor diagram. So, before going into the phasor diagram of transformer, there are some important points which must be kept in mind. Okay. You have to know some points before going into the phasor diagram of transformer. So, that is based on these points, we will draw the phasor diagram for no load, lagging load and leading load conditions of the transformer. So, those important points are: first one is transformer when excited at no load only takes excitation current. Okay, only takes excitation current. So, which leads the working flux by historic angle, that is alpha. Okay, transformer when excited at no load only takes excitation current, which leads the working flux by historic angle alpha. Okay, next. So, when the excitation is made up of two components, so the excitation current is made up of two components. One in phase with applied voltage, V is called core loss component, and another in phase with working flux phi is called magnetizing component. Okay, excitation current is made up of two components. One in phase with applied voltage V, that one is called core loss component, and another in phase with working flux phi is called magnetizing component. Okay, these are represented with the letters, that is I suffix C and I suffix M, IC and IM. Next, coming to the next one is electromotive force created by the working flux. So, the working flux phi is created the electromotive force, that is EMF, which lags behind it by 90 degrees. Okay, EMF created by working flux phi, it lags behind it by 90 degrees. So, when the transformer is connected with a load, so after now we discussed about the no-load condition and coming to the on-load condition. So, when transformer is connected with a load, it takes extra current I dash from the source, so that N into I1 dash, so N1 I dash is equal to N2 I2. So, where I dash is called load component of primary current, load component of primary current. So, under load condition, I1 is the primary current. So, each phasor sum of I dash and excitation current. Okay, I dash and excitation current. Okay, that is IE. Excitation current is IE. Okay. Next, this is the diagrammatic representation of a single phase transformer. So, you already know this one. So, here we are taking a transformer. So, it consists of a magnetic core that is represented in this diagram like two vertical lines, and so in between this we have two windings, one is primary and one is secondary. So, in this diagram the primary winding is placed on the left side and the secondary winding is placed on the right side. So, we have N1 number of turns in the primary winding and N2 number of turns in the secondary winding. So, this primary winding is connected to the supply voltage, that is V1, and next we have the EMF, that is E1, and we have the current, that is IE, that is the excitation current IE, and next we have the secondary winding. So, the secondary winding also consists of the number of turns N2 and the EMF E2 and the terminal voltage VL or V0. Okay, VS, secondary voltage. Okay, like that we have this one. And next, so this is for a practical transformer on no load condition. So, this diagram is for the practical transformer on no load condition. That is the first case. Okay, practical transformer on no load. So, the diagram is like this. So, no load means the secondary winding is open. So, actually, for a normal transformer, basic transformer, the secondary winding is connected to the load. Okay, but here I am taking the practical transformer on load condition. That means we don't consider the load that means the secondary winding is in the open condition. So this is a practical transformer on no load condition diagram. Okay, I will explain this one by one. So in this one, if the primary winding is connected to an alternating voltage, that is V1. So if the primary winding is connected to an alternating voltage, that is represented in the left side of this diagram. So secondary winding is left open, that is represented in the right side of this diagram. Okay, primary winding is connected to an alternating voltage and the secondary winding is left open. Then the transformer is said to be on no load. Okay, and next. So here I am taking the let supply voltage to V1 volts, that is connected to the primary winding. So this causes an alternating current to flow through the primary. Okay. Next, since the secondary is open, then this current is called no load primary current, that is I0. Since the secondary is open, this current is also called no load primary current. Okay. So whenever the supply voltage we have, so this causes an alternating current to flow through the primary, and the secondary is open, means the current is called no load primary current, that is I0. Okay, this I0 establishes a flux phi. Okay, this I0, that is the no load primary current, establishes a flux phi in the core. Thus I0 is not at 90 degrees behind V1. Okay, I0 is not at 90 degrees behind V1 but lags it by an angle phi naught, that is less than 90. Okay, so I0 is not at 90 degrees behind V1 but lags it by an angle phi naught less than 90. Okay, so here the no load input power, that is P naught, is equal to V1, that is the supply voltage, into I0, that is the no load primary current, into cos phi naught, that is the power factor. Okay, cos phi naught, no load power factor. So here I0 has two components. I0, that is the no load primary current, consists of two components. One is magnetizing current, that is also called as working component, magnetizing component or wattless component, like that. So it is represented with I suffix mu, and working component, that is IW. It is wattful component. Okay, magnetizing component and working component. If you know these two, that is I mu and IW, you have I0 value, that is no load primary current value in the no load transformer. Okay, firstly I will discuss the magnetizing component, and next I am going to discuss working component. Okay, so firstly magnetizing component. So this component is known as magnetizing component because it is actually used to magnetize the core of the transformer. Okay, to magnetize the core of the transformer, we have to take this magnetizing component. So we can also say that I mu is used to set up flux phi m in the core. Okay, you can also say that I mu is used to set up flux phi m in the core. Now, as the flux phi m is developed by the I mu, okay, so they both will be in phase to each other. That is I mu and phi m. Both are in phase to each other as shown in the phasor diagram. So I will show the diagram. And this current I mu is also called reactive component or wattless component of no load current, because this component does not consume active power. Okay, and it is not responsible for any losses in the circuit. Okay, the current I mu, that is the magnetizing component, is also called reactive component or wattless component of no load current, because this component does not consume active power, and it is also not responsible for any losses in the circuit. Okay, I will show the phasor diagram. Okay, next coming to the working component. So this current, that is IW, is basically responsible for the losses in the transformer. So previous component, that is the magnetizing component, is not responsible for the losses in the transformer, but this working component is responsible for the losses in the transformer. So mainly it is responsible for the hysteresis and eddy current losses. Mainly, it is responsible for the hysteresis and eddy current losses, but it also responsible for the negligible I square losses, I square R losses, that is copper losses. I square R losses, and it is also responsible for the negligible I square R losses. So this I square R losses are takes place due to the winding resistances. Hence they are negligible in no load condition. Hence they are negligible in no load condition. So as we know that this component is responsible for the losses in the transformer, and it actually does some work in the transformer. Okay, actually does some work in the transformer. Hence it is called working component or active component or fractional component of no load current. Okay, we have so many names for this one. One is already working component, and another one is active component, and another one is fractional component of no load current. Okay, so this IW is in phase with the applied voltage V1. Okay, in this one the working component is in phase with the applied voltage V1. Okay, next. So here we have the relationship equations of those things. That is IW, that is equal to I naught cos phi naught. So where cos phi naught is the no load power factor, and I mu is equal to I naught sin phi naught. This is the magnetizing component, and IW is the working component. Okay, IW is equal to I naught cos phi naught, where cos phi naught is equal to no load power factor, and I mu is equal to I naught sin phi naught. So from equations 1 and 2 we have I naught is equal to root of IW square plus I mu square. Okay, this is the no load primary current value in the transformer no load condition. I naught is equal to root of IW square plus I mu square. And next, coming to the phasor diagram of this condition. So now we will draw the phasor diagram of transformer under no load condition in few steps. Then by combining all the steps together, we will draw a final figure. Okay, so that means now I am going to discuss this phasor diagram in step-by-step manner. So this method will be very easy to understand if we discuss in a step-by-step manner. Okay, so in the step 1, I am taking the flux phi m as the reference phasor. Okay. So in the step 1, I am taking the flux phi m as a reference phasor, and in the step 2, EMF equation of no load transformer is given by, that is phi is equal to phi m sin omega t. So actually flux phi is equal to phi m into sin omega t. By using this we have E1 is equal to E1 m sin of omega t minus pi by 2, and E2 is equal to E2 m sin of omega t minus pi by 2. These are the EMF equations. Okay, EMF equations of no load transformer. In this one we have phi is equal to phi m sin omega t. So since the EMF E1 and E2 are induced by the same flux phi m. Okay, E1 and E2 are induced by the same flux phi m. So they both will be in phase to each other. They both will be in phase to each other. That means E1 and E2 are in the same phase. But E2 will differ in magnitude from E1. So but the E2 will differ in magnitude from E1 because, so you know, A is equal to, that is area of cross section, A is equal to E1 by E2, that is equal to T1 by T2. So from this one I am writing E2 is equal to E1 by A. This is the only difference between E2 and E1 in the no load transformer. By using these two steps we will draw the phasor diagram. Okay, so from the above equations we can also conclude that both EMFs E1 and E2 lag behind the flux phi m by 90 degrees as shown in the figure. So firstly, in the first step, I am taking the flux phi m as the reference phasor. So this orange color line we have. So this is the reference phasor. Okay, I will draw first this line phi m line, and next, so the E1 and E2 lines are combined added to this line. So here the E1 and E2 are both in same phase. That means both are in the same line. But here the phi m, that is the flux, lags the E1 and E2 by 90 degrees. So exactly 90 degrees, that is perpendicular to each other. Okay, the phi m line is lagging E1 and E2 line by 90 degrees. So this is the lagging condition. So firstly I will take the reference phasor phi m. So for the phasor phi m, reference phasor phi m, I will draw the E1 and E2 line. But here E1 and E2 are in the same phase. But this E1 and E2 line lag behind the flux by 90 degrees. So this is the diagram for the first two steps. Okay, next coming to the third step. So here the voltage drops in the primary windings are very negligible in this case. So at no load condition the voltage drops in the primary windings are very negligible in this case. So we can neglect them. So we can neglect the voltage drop. Hence E1 will be equal to the applied voltage V1. Okay, E1 will be equal to the applied voltage V1, and according to the Lenz law, it is also opposite to the applied voltage. So according to Lenz law, so the Lenz law states that the supply voltage or applied voltage is always opposed with the induced EMFs. Okay, according to this law, it is also opposite to the applied voltage V1. That is V1 is phase opposition with the V1. Both are the same line, but is in the phase opposition. That's why I draw a V1 line which is connected this phi m and E1 E2 line, but I am giving different direction, opposite direction to the E1 and E2. That's why I am taking the symmetrical line into opposite direction. But all are in the same line, E1 E2. But E1 E2 in the same direction, E1 in the opposite direction. Okay, so this is the step 3, and coming to the step 4. So we have already discussed that I mu will be in phase with the flux phi m. So I already discussed it in the components of I naught, working component and magnetizing component. So the magnetizing component will be in phase with the flux phi m. That's why I draw a line, I mu line in the reference phase of phi m. I am indicated the I mu direction towards the phi m. That is, these two are same direction. That's why I am drawing a line to the phi m in the same direction. That means I mu will be in phase with phi m. Okay, so both are in the same direction. Why? Because these two are in phase. Next, and IW is in phase with the applied voltage. So based on the second one, that is a working component. So that one, the IW is in phase with applied voltage V1. That's why I am taking the IW line in the V1 line. So already we drawn V1 line. For that line I am adding this IW. This V1 and IW is in phase with each other. That means both in the same direction. So IW and V1. That's why I am drawing this IW. Okay. So this is step 4, and come to the step 5. So now take the phasor sum of I mu and IW. So you know already the no load primary current is the summation of I mu and IW. So it will be I naught. So take the phasor sum of I mu and IW. It will be I naught as shown below. So by combining these two phasor sums, I am taking the phasor sum of this IW and I mu. This is I naught. Okay, the combination of IW and I mu we call it as no load primary current. That's why I am taking this blue line. I am adding these two. So that's why we have I naught. Okay. So this is the complete phasor diagram for when the transformer are no load condition. Firstly, I am taking the reference phasor, that is phi m. So for this reference phasor, I am taking E1 V2 line. So this E1 V2 both are equal. That means both are in the same phase, but it lags phi m by 90 degrees. That's why I am taking this line below the phi m line. This is the lagging condition, and after that I am taking the voltage, terminal voltage V1. So according to Lenz law, the supply voltage is always opposite the induced voltages or induced EMFs in the system or in the circuit. That's why I am taking the V1 line. It is a phase opposition with the E1 and E2 line. That's why I am taking this line V1. And I am taking the components of I naught, that is IW and I mu. So from the concept of working component and magnetizing component. So I mu is always in phase with the phi m, and IW is always in phase with the V1. That's why I'm taking I mu and IW is in phase with IW, I mu is in phase with the phi m. That's why I'm taking the I mu line in the phi m and IW in V1. Okay, both are in the same direction. And after combining these two IW and I mu, we have the primary, no primary current, that is I naught. So this is the line we have. Okay. So this is the phasor diagram of transformer on no load condition. No load condition. And next coming to the, so this is the final diagram we have. So combine all the above steps. That is the all 5 steps combined to get the actual phasor diagram. So an approximate phasor diagram for a transformer under no load condition is like this. Okay. Here the angle between the IW and I naught is phi naught. Okay. That is no load power factor. Okay. So we can conclude some results from the phasor diagram. That is, I already discussed. IW is equal to I naught cos phi naught, and IB is equal to I naught sin phi naught. So finally, I naught is equal to root of IW square plus I mu square. So from this one, I am writing cos phi naught. That is the no load power factor. Cos phi naught is equal to IW by I mu. That is working component by magnetizing component. So as the angle is phi naught, so power factor will be cos phi naught. So also core loss is equal to V1 I naught cos phi naught, that is equal to V1 IW, that's I naught cos phi naught, you know already IW. Substitute here. Finally we have the core loss is equal to V1 into IW. So magnetizing volt amperes is equal to V1 I naught sin phi naught. So this will rewrite as, you know already I mu is equal to I naught sin phi naught. So magnetizing volt amperes or reactive volt amperes is equal to V1 I mu VAR, volt ampere rating. Okay, volt ampere reactive. Okay, so this is the explanation for the phasor diagram of transformer on no load. And coming to the second case, that is the transformer on load. So here, when the secondary winding is connected to a load. So in the previous case, the secondary winding is not connected to the load. That's why we are taking the secondary winding on as open. So here, when the secondary winding is connected to the load, then the transformer is said to be on load. This is the diagrammatic representation of this case. So here I am taking one magnetic core and primary and secondary windings. So here the primary winding on the left side is connected to the supply voltage, that is V1. It consists of primary current I1. It also consists of the induced EMF E1. And coming to the secondary side, that is in the left side of this diagram. So right side of this diagram we have, so it consists of E2, that is the induced EMF in the secondary winding, and I2, that is the secondary current, and this one is connected to the load. The secondary winding which is connected to the load is called secondary winding. The winding which is connected to the load is called secondary winding. And in the transformer and non-load condition, the secondary winding is connected to the load. So it consists of E2 voltage, that is the terminal voltage or load voltage, and I2 is the secondary current. So this is the diagrammatic representation of transformer load condition. Next, so due to this load condition, the secondary current I2 is flowing through the load. So here the secondary winding is connected to the load. That means the secondary current I2 is flowing through the load. It is already shown in the diagram. Okay, this is the diagram. So the current I2 is flow through the load. Okay. So the phase angle between V2 and I2, the phase angle between V2 and I2 depends on the type of load. Why? Because the current is flowing through the load. That's why the phase angle between V2 and I2 depends on the type of load. And when the load is resistive, so actually we have three loads. One is resistive, and another one is capacitive, and third one is inductive. So when the load is resistive, I2 will be in phase with V2. Okay, please concentrate on these 3 points. So when the load is resistive, that is I2 will be in phase with V2. So when the load is inductive, I2 will be lagging V2. And when the load is capacitive, I2 will be leading V2. I2 will be leading V2. So the figure shows the transformer under no load condition. I will show the diagram. It shows that the transformer under no load condition. So here the primary winding draws no load current I0. So this I0 sets up flux phi. So So you already know these points, but in this condition also I will discuss this one. So here I am showing you the diagram. The diagram is for transformer under no load condition. Okay, this is the diagram. So here I am taking the transformer which consists of magnetic core. It is in rectangular shape, and we have the two windings. One is primary and one is secondary. The primary winding is connected to the supply, and the secondary winding is in the open condition for the no load condition. For the load condition, the secondary winding is connected to the load. That's why we have I2 is now equal to 0. Here the secondary winding is in open condition. There is no secondary current, that is I2 is equal to 0. But we have I0, that is no load primary current we have, and E1, that is the induced EMF in the primary winding, and E2, that is the induced EMF in the secondary winding, and V2, that is the terminal voltage, and V1 is the supply voltage, and phi is the flux. This is the circuit diagram for the transformer on no load condition. So here I am taking one more. So here the figure shows the transformer under load condition. So this is the transformer under load condition. So here the secondary current I2 produces flux phi2. So here the secondary current I2 produces flux phi2, and this flux phi2 opposes the no load flux phi. So if you observe this diagram, we have a dotted lines in the magnetic core. So one is two dotted lines actually we have. One is for the main flux no load flux phi, and another one is for the secondary flux phi2. But these two fluxes are opposing each other. Okay. Here the secondary current produces flux phi2. So this flux phi2 opposes the no load flux phi and decreases the no load flux. Okay, and decreases the no load flux. It is shown in this diagram. So if you observe this diagram, same we have the magnetic core and we have the two windings, primary and secondary. So in the load condition, the primary winding is connected to the supply voltage and secondary winding is connected to the load. Okay, so the primary winding consists of V1, I0 and E1, and the secondary winding consists of E2, I2 and phi2. Okay, so here V1 is the supply voltage, E1 is the induced EMF in the primary winding, and I0 is the no load primary current, and here E2 is the induced EMF in the secondary winding, and I2 is the secondary current. Okay, and phi2 is the flux produced by the secondary current I2, and phi is the flux produced by the no load primary current I0. Okay. So next, so due to this induced EMF E1 is reduced. Due to this, so actually induced EMF E1 is reduced because the flux phi is reduced. Okay, so due to this induced EMF E1 is reduced and V1 dominates over E1. So V1 dominates over E1. So V1 is the supply voltage and E1 is the induced EMF in the primary winding. So that V1 dominates E1 and thus causes additional current I2 dash. Okay, so after decreasing the phi, so induced EMF E1 is reduced and V1 dominates over E1 and thus causes an additional current I2 dash to flow through the primary. So actually we have the I0 current only, but after reducing the flux, E1 also reduces and V1 dominates the E1. At that time, it causes additional current, that is I2 dash, that will flow through the primary. So this I2 dash is also known as load component of primary current. I2 dash is also known as load component of primary current. Okay, next this current is in anti-phase with the I2. That is opposite direction with the I2. And I2 dash establishes a flux phi2 dash. Okay, I2 dash establishes a flux phi2 dash. Okay, and this flux phi2 dash is equal in magnitude but in the opposite direction of phi2. Okay, this flux phi2 dash is equal in magnitude but in phase opposition, but in the opposite direction of phi2. Okay, hence phi2 dash and phi2 cancel each other because opposite direction. Phi2 dash and phi2 cancel each other. I will show the diagram, after that you will understand. Okay, so this is the diagram I am taking. So here we have additional flux, that is phi2 dash, and additional current we have, that is I2 dash. So because of this I2 dash, we have the phi2 dash. Okay, so this phi and phi2 dash are in the same direction and phi2 is in the opposite direction. That means this phi2 and phi2 dash are cancel each other. Okay, so this is the I2 dash current and phi2 dash flux. Additionally we have in this diagram. Okay, And next, so here after cancelling each other, that is phi 2 dash and phi 2, we have finally we have the flux phi, that is the primary winding flux, that is phi. Only phi is present. So this is the diagram representation of that explanation. So after cancelling phi 2 dash and phi 2, we have the flux phi. Okay, here we have the I1 is equal to primary current, I1 is equal to I0 plus I2 dash. Okay. Next, thus when the transformer is loaded, the flux passing through the core is same. Okay, when the transformer is loaded, the first case is the flux passing through the core is same as that at no load. Okay, the flux passing through the core is same as that at no load. That is, flux is constant at no load as well as loaded condition. Okay, flux is constant at no load as well as loaded condition. So that is why transformer is called a constant flux operator. A constant flux operators. And the total primary current I1 will be vector sum of I0 plus I0 and I2 dash. So the total in the previous diagram you have already seen that one. The total primary current I1 is equal to I0 plus I2 dash. Okay, that is the total primary current I1 will be vector sum of I0 and I2 dash. And coming to in this concept I will discuss two parameters of the transformer. One is transformer winding resistance and another winding is transformer winding reactance. So first I will discuss transformer winding resistance. So in the practical transformer, the windings have some resistance. You already know this point. So the primary winding has primary resistance. It is denoted as R1. Similarly, the secondary winding has secondary resistance. It is denoted as R2. And the diagram is like this. So this is a diagram for the transformer winding resistance. Okay. So here we are considering a transformer which consists of the magnetic core and the primary and secondary winding. So the primary winding consists of some resistance. That one is now represented with R1, and the secondary winding is also consists of some resistance. It is also represented with R2. Okay. So coming to the transformer winding leakage reactance. So in practice, all the flux generated by the primary winding does not link into the secondary winding. Okay, all the flux generated by the primary winding does not link to the secondary winding in the practice. So some part of the flux passes through air rather than around the core. Okay, some part of the flux passes through air rather than around the core. So this flux is called primary leakage flux. It is denoted by phi L1. Okay, this flux does not link with the secondary winding. That's why we will call it as leakage flux. Okay, this flux induces an EMF EL1 in primary winding. The flux phi L1 is in phase with I1. Okay, this flux phi L1 is in phase with I1. So similarly, a leakage flux is set up in the secondary winding. This flux is known as secondary leakage flux. It is denoted as phi L2. Okay, and this flux induces an EMF EL2 in secondary winding, and the flux phi L2 does not link with the primary winding. Okay, the flux phi L2 does not link with primary, and it is in phase with I2. It is in phase with I2, that is phi L2 is in phase with I2, and the secondary leakage fluxes are shown here. So this is the diagrammatic representation of this explanation. So here we are considering a transformer which consists of magnetic core and the windings, primary and secondary. So this primary winding consists of flux phi L1 and EL1, but here some fluxes does not link with the primary, that one is called phi L1. Okay, and similarly in the secondary winding some fluxes not linking with the primary, that one is called leakage flux, that is denoted as phi L2. And we have the this flux phi L1 is indices EL1, and this flux phi L2 indices EMF EL2 in the secondary, and this phi L2 is in phase with I2, and phi L1 is in phase with I1. Okay, like that we have this diagram. Okay, we have the total flux phi. Okay, and next, so at no load and light loads, okay, at no load and light loads, the transformer carries only small current. Okay, at no load and light loads, the transformer carries only small current, and hence leakage fluxes are negligible. Okay, leakage fluxes are negligible. So under heavily loaded conditions, the transformer primary and secondary windings carry large current. Okay, under heavily loaded conditions, the transformer primary and secondary windings carry large current. Okay, due to this, the leakage flux increases under heavy load. Under light load, the leakage flux are negligible. Okay, and in the heavy conditions, the leakage flux is increasing. Okay, so the primary leakage reactance X1 and secondary leakage reactance X2 are indicated in the figure. I will show another diagram. So in the diagram, I will show the primary leakage in the reactance X1 and secondary leakage reactance X2. And from the above discussion, the practical transformer should have winding resistances and leakage reactances, that is R1, R2, X1 and X2. So this is the diagram we have. So we have X1, X2. This is the reactances. And this is the transformer. It consists of one magnetic core and the two windings. Okay, the primary winding consists of some reactance, that is X1. And the secondary winding consists of some reactance, that is X2. Okay. And this is the combination of R1 and X1, resistance and reactance. For the primary and secondary, R1, X1, and the secondary R2, X2. So for the primary, we have the R1, X1, and for the secondary, we have R2, X2. This is the diagram representation of this explanation. And so coming to the vector diagram of transformer on load condition. So here I am discussing the vector diagram of transformer on load. So this is the diagram representation of that one. So here I am considering a transformer. Okay. So here I am taking the primary winding and secondary winding. In between we have the magnetic core. So the primary winding consists of E1 and the secondary winding consists of E2 in these units. And it consists of resistance and reactance R1 and X1 and current I1 and voltage V1. And in the second step we have I2, R2, X2 and V2, E2. And general there is the load impedance. Okay. And so the figure shows practical transformer on load. Okay. We shall consider two cases for this one. So firstly, when such a transformer is assumed to have no winding resistance and leakage reactance. So when such a transformer is assumed to have no winding resistances and leakage reactances. In the second case, when the transformer has winding resistances and leakage reactances. So first I will consider the first case. So in this one I am assuming no winding resistances and leakage reactances. That is R1, R2 from the diagram. R1, R2, X1, X2 are neglected. Okay. So I will show the diagram. So the diagram shows a practical transformer with the assumption that resistances and leakage reactances of the winding are negligible. So this is the diagram representation of that one. So here I am not considering R1, X1 and R2, X2. The diagram will show like this. Okay, here we have V1, I1, E1, E2, I2, V2, ZL. Here I am writing R1, X1, R2, X2. Okay. Next, so with this assumption, V1 is equal to E1 and V2 is equal to E2. However, if the V1 is equal to E1, that means V1 and E1 are 180 degrees out of phase. So that means there is some opposition. Okay. So we consider an inductive load. So here I am considering an inductive load. So that means the secondary, that means lagging load. Inductive load is nothing but the lagging load. Capacitor load is nothing but the leading load. And resistor load is nothing but the constant load. Okay. So after considering the inductive load, the secondary current I2 is lagging with respect to V2. The secondary current I2 is lagging with respect to V2 by an angle phi 2. Okay. Next, the primary current I1 must meet two requirements. The primary current I1 must meet two requirements. One is it must supply the no load current I0 to meet the iron losses in the transformer and to provide flux in the core. And second one, it must supply a current I2 dash to counteract the demagnetizing effect of secondary current I2. Okay, so the magnitude of I2 dash will be such that the magnitude of I2 dash will be such that N1 I2 dash that is equal to N2 I2. So from this one I am writing I2 dash is equal to N2 by N1 into I2. So you know already from the transformer ratio N2 by N1 is equal to K up to here. Finally we have I2 dash is equal to K K into I2. So the total primary current I1 is the vector sum of I2 dash and I0. So that is I1 is equal to I0 plus I2 dash bar. So here I2 dash is 180 degrees out of the phase with I2. Out of phase with I2. Okay. Next. So here I will draw the diagram for the both the cases. Okay. So vector diagram of transformer load. So here I will show the diagram. So the figure shows the vector diagram for. I will show three diagrams. Those diagrams for unity power factor, lagging power factor, leading power factor. That means unity power factor for resistive load, lagging power factor for inductive load, leading power factor for capacitive load. Okay. So I will follow some steps to draw this vector diagram for the transformer on load condition. First step, in this one I am drawing the flux line phi, so that is the reference phase, reference vector. Okay, in the slides, earlier slides, I show some step-by-step procedure to draw the phasor diagram of transformer on no load condition. In this one also I am taking the flux line as the reference phasor. Okay, so here also I am taking the for the vector diagram. Here also I am taking the flux line phi as the reference vector. So in every diagram for unity power factor and for lagging power factor and for leading power factor, I am taking the flux phi line as the reference phasor, reference vector. So this is for vector diagram. So this is okay. In all three diagrams, I am taking phi as the reference vector. Okay. Next, in the second step, I am drawing the V1 vector. I am drawing the V1 vector, that is V1 line I will draw. So, but the angle between flux phi and V1 is 90 degrees. Okay. So, in the lagging power factor, the V1 lags phi by 90 degrees, and for leading power factor, the vector V1 leads the flux phi by 90 degrees, and for unity power factor, V2 and I2 are in phase. That means equal, are in same phase. That's why if you observe the diagrams, so for the unity power factor, V1 and phi are exactly 90 degrees. Exactly 90 degrees. And in the lagging power factor, flux phi lagging the V1 is some angle. Okay. Lagging the angle some one. Okay. Next, in the leading power factor, the flux phi is leading V1. Okay. Next, after drawing the flux line phi and V1 line, I am going to draw the induced EMFs E1 and E2 vector. So, in this one, the V1 opposes E1 by 180 degrees out of phase. 180 degrees out of phase. So, that is shown like this. So, here the V1 lags E1 out of 180 degrees in all the three diagrams. Same process. But in all three diagrams, E1 is equal to E2. E1 is equal to E2. But only V1 is 180 degrees out of phase. 180 degrees out of phase. That's why I am drawing E1 in the same direction. V1 in opposite direction, but in the same line. But it lags, but it has 180 degrees phase difference in all the three diagrams. Okay, like this we have. And next, coming to the fourth step, here I am drawing the nodal primary current I0. I am drawing the nodal primary current for all the three cases, for unity power factor, for lagging power factor and leading power factor. Here the current I0 is lagging with respect to V1. Okay, I0 is lagging with respect to V1 by an angle phi naught. Okay, I0 is lagging with respect to V1 by an angle phi naught. So here. Okay, like this we are drawing. So in all the three cases. Okay, in all the three cases, the I0 is lagging with respect to V1. The I0 is lagging with respect to V1. This I0 is lagging V1 with an angle phi 1. Okay, phi 0, sorry, not phi 1, it is phi 0. And next, fifth step, draw the secondary current I2. So, for this case, I am taking the secondary current I2, that means for the UPF, that is unity power factor, V2 and I2 are in phase. V2 and I2 are in phase. So, if you observe the unity power factor vector diagram, so here I2 and V2 are in same direction. Okay, for lagging power factor, I2 and V2, so that V2 is lagging I2 by angle phi 2, and for the leading power factor, V2 leads the I2 at an angle phi 2. V2 leads I2 at an angle phi 2. Okay, this is the explanation for the fifth step. Okay, and next, coming to the sixth step. So in the sixth step, I am going to draw the load component of primary current, that is I2 dash. Load component of primary current I2 dash. So actually it is opposite and equal in magnitude to I2. Okay, it is opposite and equal in magnitude to I2 in all the problems, in all the diagrams. So this is the I2 dash. But this I2 dash is equal and opposite to the magnitude of I2. This I2 dash is equal and opposite to the I2. So that means I2 and I2 dash are in the same line but in opposite direction. So if you observe these three diagrams, you will understand. So in the unity power factor line, I draw a line. I am indicated with I2 dash, but it is in opposition with the I2. That means I2 in one direction, I2 dash in another direction. But these two in the same line. But in the unity power factor and lagging power factor and leading power factor also. If you observe this diagram, you will understand. Same line but opposite directions. Okay. And next, coming to the seventh step, in this one I am drawing the primary current I1. Primary current I1. So this current is lagging with respect to V1 by an angle phi 1. So I1 is lagging with respect to V1 by an angle of phi 1. And I1 is the vector sum of I2 dash and I0. Okay. So in this one, in the seventh step, I am drawing the primary current I1. So this current lagging with respect to V1 by an angle phi 1 in all the cases. In all the cases, primary current I1 lagging with respect to V1 by an angle phi 1. This I1 is the vector sum of I2 dash and I0. So if you observe this one, you will understand. So here, this I1 is lagging V1 at an angle phi 1. So V1, I1, phi 1. So V1, I1, phi 1. In all the cases, we have this type. Okay. So here I am combining I2 dash and I0. Finally, we have the I1 in all the three diagrams. I am combining I2 dash I0 and finally we have the I1. I2 dash I0 and finally we have I1. Okay. So these are the vector diagrams for the transformer on load conditions. Okay. And coming to the case 2. So transformer with resistances and leakage reactances. So here I am considering the R1, R2, X1 and X2. Okay, here I am considering. So in the previous case I am neglecting the R1, R2, X1 and X2. So in this case I am considering R1, R2, X1 and X2. The diagram is like this. Here we have the voltage drops I1, R1, I1, X1 and I2, R2 and I2, X2 like this. This is the diagrammatic representation of this explanation. Okay. Next. So here I am drawing a vector diagram for the second case. So here already the figure shows a practical transformer having winding resistances and leakage reactances. Okay, R1, R2, X1, X2. So here the input voltage is applied to the primary winding. That's why current I1 is flowing through the primary winding. And there is a voltage drop in R1 and X1. So the primary induced EMF E1 is less than the input voltage V1. Okay, after the input voltage is applied to the primary winding, it produces I1 and this I1 current is flowing in the primary winding, and we have the voltage drop in R1 and X1 on the primary side. So the primary induced EMF E1 is less than the input voltage V1. So E1 is less than V1, and the load is connected in the secondary side. That means current I2 flowing through the load. Okay. Next, there are voltage drops in R2 and X2. So the secondary terminal voltage V2 is less than secondary individual EMF V2. That means E2 is greater than V2 in the secondary winding. So in the secondary side, the load is inductive load. That means lagging load. And so the secondary current I2 is lagging V2 by an angle phi 2. Okay, the secondary current I2 is lagging V2 by an angle phi 2. So if the load is capacitive, means I2 will be leading V2 by an angle phi 2. So if the load is capacitive, that is leading. That is I2 will be leading V2 by an angle phi 2. And next, if the load is resistive, then I2 and V2 are same phase. And the primary current I1 must meet two requirements. Must meet two requirements. Must meet two requirements. So the primary current I1 must meet two requirements, that is, it must supply the no-load current I0. So it must supply the no-load current I0 to meet the iron losses in the transformer and to provide flux in the core. And it must supply a current I2 dash to counteract the demagnetizing effect of secondary current I2. So you know already these things. So the magnitude of I2 dash will be such that N1 I2 dash is equal to N2 I2. From this one I am writing I2 dash is equal to N2 by N1, that into I2, and I2 dash is equal to K into I2. You know from the transformer ratio, N2 by N1 is equal to K. So here I2 dash is 180 degrees phase shift of I2. I2 dash is 180 degrees phase shift of I2. Then the total primary current I1 is the vector sum of I2 dash and I0. That is I1 bar is equal to I0 plus I2 dash. Okay. Next, so from these things, after adding the resistance and reactances, we have the voltage drop sector as the resistance, and in the reactance in both the primary and secondary. So voltage drop across the resistance, that is R1, we have I1 R1, and voltage drop across the reactance, that is X1, that is J into I1 X1, and finally we have the voltage drops, that is total voltage of V1 is equal to I1 R1 plus J into I1 X1 plus E1. So from this one I am rewriting this equation as E1 plus, here I am taking the common of I1. So after that, after coming the I1 we have I1 of R1 plus JX1, and you know already the combination of R1 and JX1, that one is Z1. So finally we have V1 is equal to E1 plus I1 Z1. Okay, next here the Z1 is the total impedance in the primary. And coming to the secondary winding, similar to the primary, the voltage drop across the resistance, that is I2R2, and the voltage drop across the reactance, that is J into I2X2. And from this one I am writing V2 is equal to V2 plus I2R2 plus J into I2X2, and V2 plus, here I am taking the common factor, that is I2, and we have R2 plus JX2, and V2 is equal to V2 plus I2. Here R2 plus JX2 is the Z2, or V2 is equal to E2 minus I2 Z2. V1 is equal to E1 plus I1 Z1, and V2 is equal to E2 minus I2 Z2, or E2 minus V2 is equal to I2 Z2. Here Z2 is the total impedance in the secondary. Okay. Next, coming to the phasor diagram, this is the main we have. So coming to the phasor diagram of transformer on load, here also we are going to take some steps, follow some steps to draw the phasor diagram for the different power factors. That is unity power factor, leading power factor, and lagging power factor. So in the step 1, I am taking the flux line, that is phi. So it acts as a reference phasor. So it is indicated with the points OA. OA. In all the three diagrams, the OA line is the flux line. In all the three diagrams, OA line is the flux line. So in all the three, so in the unity power factor, OA line represents the flux line, and in the lagging power factor, OA line is indicated the flux line phi, and in the leading power factor, OA line represented with the flux line. That is the first step. I am taking the flux line as the reference phasor. And coming to the second step, I am drawing the individual EMF line E1, that is OB, in all the three cases. but the angle between E1 and phi is 90 degrees lagging in all the cases. In all the cases, the angle between E1 and phi is 90 degrees lagging. That is OB line. That is OB line. So this one, OB line. So this is in all the cases, this OB line, that is E1 is lagging with an angle 90 degrees with respect to flux. Okay, in all the three diagrams, the OB line is in the below the flux, that is the below to the flux line. Okay, okay, like this we have. And next, coming to the third step. So here I am drawing the minus E1 line. So this is the opposite to the E1 line. So here I am drawing the minus E1 line. So it opposes to E1 in all the three cases. That is represented with the OC point, OC that is opposite to E1. So this one. It is indicated with the OC line, this one. So here minus E1. In all the three cases I am drawing this one, OC line. It is opposite to E1. Okay. Next, coming to the fourth step, here I am drawing the no-load primary current, that is I0. It is indicated with OD point, OD, in between OD. We have the no-load primary current. In all three cases we have OD. OD, that is the I0 in all three cases. I0. Okay, I0, OD. And next, coming to the step 5, here I am drawing the secondary terminal voltage V2. So in the fifth step, I am drawing the secondary terminal voltage V2 in the particular direction of OE. In the particular direction OE. So I am drawing the secondary terminal voltage for the three cases. Unity, lagging and leading. It is represented with the OE. OE. Okay. V2 line. So this one. OE in all the three cases. OE. That means V2 line. Okay. OE. That is V2 line. And next, coming to the step 6. Here I am drawing the secondary current I2. That is OF line. But after we discussed flux and induced EMF E1 and minus E1 line and primary current I0 and terminal voltage V2, these all are same for all the cases. Same for all the cases, for the unity and for the lagging and for the leading. But this I2 line is different for each case. For the unity power factor we have the different, and for the lagging power factor we have a different combination, and for the leading power factor we have a different combination. That is for the unity power factor, I2 and V2 are in phase. So if you observe this V2 for the unity power factor, this I2 line is in phase. It is in the same direction of V2 for the unity power factor, and for the lagging power factor, this I2 lags V2. Okay, this I2 is lags V2 by an angle phi 2. Okay, and for the leading power factor, this I2 lags V2 by an angle phi 2. Okay, by an angle phi 2 leading. For the three cases it is different. Okay, coming to the seventh step. In this step I am going to draw the I2R2 drop line. So this drop line is parallel to the current vector I2. So it is indicated with the letters EG. So in the seventh step I am drawing I2R2, and in the eighth step I am drawing I2X2 drop line. So this I2R2 drop line is parallel to the current vector I2, and this I2X2 drop line is perpendicular to the current vector I2. So that's why, so here I2R2 drop line is represented in the phasor diagram in all the three cases. That is indicated with the EG. Okay, it is indicated with the EG. So this line, I2R2, EG in all the cases, EG, and I2X2 drop indicated with the GH line in all the three cases. This is I2X2 drop. I2R2 is EG and I2X2 drop is GH in all the three cases. All three cases same. Okay. Next, coming to the ninth step. So I2X2 line is joined with E1 line. So in this 90 step, I am joining I2X2 line with the E1 line. That is E2 line. That is represented with OH. In all the three cases, we have this OH line. In all the three cases, we have this OH line. So this one, OH line. So here I am combining which one? Here I am combining I2X2 line with E1. I2X2 line with V1. Okay. That's why in all the cases we have this line. Okay, next. In the 10th step, I am drawing the I2 dash line. So here the I2 dash is opposes the I2 line. I2 dash is opposing the I2. That is 180 degrees out of phase. It is indicated with the letters OI. OI line is the I2 dash line in all the three cases. Okay. I2 dash is opposition. That is OI line. So this line. Okay. OI line. Okay. I2 dash line. In all the three cases we have this line. OI2 dash. So I2 dash. OI line. In all three cases we have. Carefully observe these diagrams. Okay. And coming to the 11th step, so in this step I am drawing the I1 line, that is OJ. So I1 line is the combination of, that is the vector sum of I0 plus I2 dash. Okay, that is, in all the three cases I am combining I0 and I2 dash, and finally we have the I1 dash. I am combining I0 and I2 dash in all the three cases. I0 and I2 dash I am combining, and finally we have the I1 line. In all the three cases I am combining these two. Okay. And coming to the 12th step, here I am drawing the I1 R1 drop line. I1 R1 drop line. So it is parallel to the current vector. So that is I1, current vector I1, that is, it is indicated with the letter CK. CK line is the I1 R1 drop line in the phase diagram. CK line is the I1 R1 drop line. Okay, it is parallel to the current vector I1. Okay, CK. I1 R1 drop. So this one. CK line. It is parallel with I1. And next, draw the I1 X1 drop line. It is perpendicular to current vector I1. That is the KL line. So KL line in the phasor diagram of all the three cases is represented with I1 X1 drop. Okay, KL line. So this one, KL. This one I1 X1 drop. In all of the cases we have these things. Okay. Okay, these are the different steps we have to follow to draw the phasor diagrams. Okay, thank you for watching this video. I hope you will understand this one. Okay, thank you. In the next class, I am going to discuss remaining topics.